Hello all, myself Sambasiva Rao, working as Assistant Professor in the Department of Civil Engineering at VIGNAna VJEC. Today we are going to discuss the topic stopping side distance as a part of highway geometric design. If you look at the definition of stopping side distance, it can be easily understand from here. So the minimum side distance available on the side of the driver of a vehicle to stop in front of an obstruction is said to be stopping side distance. So that can be easily the minimum side distance or the distance which is available on the side of the driver to stop the vehicle in front of an obstruction. That obstruction might be anything, either it can be an object or it can be another animal or it can be some other vehicle coming in the opposite direction. So that is what the definition of stopping side distance. So this is the initial condition of the vehicle here, okay, so which is traveling at some uniform speed, okay, and there the vehicle, the driver in the vehicle has observed an obstruction which is present over here. So the height of that obstruction is generally taken as 15 centimeters, which is nothing but 0.15 meters. And the height of the driver is nothing but capital H is equal to 1.2 meters. So this is the recommendations as per code. So the height of the driver minimum should be 1.2 meters and the height of the obstruction will be considered only if it is more than height of 15 centimeters. So the moment the driver in the vehicle has seen an obstruction, he is supposed to bring the vehicle to stopping condition if the vehicle is in static, if the obstruction is in stopping condition, so that he will not undergo any collision. So for which, okay, he will be traveling to some distance which is nothing but lag distance, okay. So in this distance, the driver will still be moving at a uniform speed till the moment he will apply the brake, because the moment immediately the driver sees an obstruction, he will not bring the vehicle to rest condition. So for that, there is some process going on in his mind. Okay, there is some time consumed by the driver in simulating some responses. So that time is nothing but the reaction time. The distance traveled within this particular time is said to be the lag distance. Okay, so in this time, the vehicle is going to travel at the uniform speed and the distance is nothing but lag distance. So the reaction time can be explained by this theory, which is nothing but PIEV theory. So this is the diagram corresponding to PIEV theory. So this is nothing but input. Okay, the input will be any stimulus. So that will be any stimulus, and the output will be response. And the output will be the response. So there will be a perception. Okay, the perception will be carried out to the brain. So this is the brain portion over here. So the perception will be carried out to the brain by means of either eye or ear. So you have seen an obstruction through an eye. So that is what your perception. So this is what your perception. Okay, and that will be carried out to your brain. So once you carry out to your brain, so this side portion will be involved in some intellectual coefficient. So that means nothing but it is telling you to your brain that there is some obstruction present in front of you, okay, and you have to do something. So that is what your intellectual coefficient is telling you, and as a result of that, there will be some emotion that is generated in you, in your brain. Okay, so as a result of that, maybe you are in anger, or whether you are hurried, or whether something, because of that there is an emotion generated in you, and you have to suppose to take a call. Either you have to stop the vehicle, okay, or else you have to come outside of the lane and go in the other lane. So that is what the emotion that is being carried in your brain. So that emotion has to be carried out as an activity. So that is nothing but volition. So that is nothing but performing an activity. So that is completely a response over here. So this is what the PIEV time, okay, or theory. The PIEV time can be obtained from PIEV theory. It means nothing but the entire process that is required for PIEV, the time is said to be the reaction time of the driver. So that reaction time of the driver is simply denoted by small t, okay, which is generally 2.5 seconds, which is recommended by the code for stopping side. Okay, in order to stop your vehicle, you need to have you are supposed to have a reaction time of 2.5 seconds. For some drivers it might be less than that, for some drivers it might be more than that, but that is the average reaction time that is should be considered. Okay, so therefore this, as I have discussed previously, that lag distance is nothing but the vehicle is going to travel at the uniform speed, because the driver did not apply the brakes. So therefore the speed, so if you look at the formula for speed is equal to distance by time, so therefore distance is equal to v into t. Okay, so this is the lag distance. I will be representing it as s suffix l, so which is nothing but v into t, where v is nothing but the design speed of the vehicle at which your vehicle is traveling, and t is nothing but reaction time of the driver. So this is the regarding the lag distance. So on the other part of the distance, which is nothing but the braking distance. Other part of the distance, which is nothing but the braking distance. So here it is nothing but you have seen the obstruction. Obstruction. So he has seen the obstruction. So this is the condition. Okay. Here applying brakes. So this is the moment at which the driver is applying the brakes, and this is stopping condition. So that is nothing but stopping the vehicle in front of the obstruction. So the distance traveled at this moment, that is said to be the braking distance. Braking distance is going to depend upon the braking characteristics of the vehicle and not going to depend upon the road user characteristics or the driver characteristics. Okay, the moment the driver has applied the brake, okay, then there should be some force which is stopping the vehicle. So basically there is an equation which is nothing but the kinetic energy in the vehicle. Kinetic energy in the vehicle should be compensated by some work done. So which is nothing but the work done in stopping the vehicle. So there should be some work done in stopping the vehicle. So that should be equivalent to kinetic energy, so that the vehicle will be coming to halt condition. So the kinetic energy of the vehicle is nothing but half mv square is equal to work done is equal to force into distance. Of course, the only force present in the here in stopping the vehicle is nothing but the frictional force between the tire of the vehicle and the road. So therefore that is nothing but frictional force F multiplied by braking distance. The distance traveled by the vehicle after applying the brakes is SB. That is nothing but the braking distance. So this is nothing but half into that m should be expressed in terms of W by G, weight by G, multiplied by V square is equal to frictional force is equal to frictional coefficient, which is nothing but longitudinal coefficient of friction. As the vehicle is moving in the longitudinal direction, we are interested only to take into consideration of longitudinal coefficient of friction multiplied by weight of the vehicle. That is nothing but force is equal to mu into weight of the vehicle. So multiplied by this distance, braking distance remains as it is. So therefore you are going to cancel out the terms W on either side. So we are interested in to calculate the value of the braking distance, which is nothing but SB. SB is equal to V square divided by 2GF. 2GF. So this is the derivation for braking distance. Of course, if you look into that derivation of the braking distance, here there is no parameter which is involved in the reaction time of the driver. So it is irrespective or independent of the vehicle characteristics, road user characteristics. But whereas if you look into that lagging distance, it is dependent upon the road user characteristics, but it is independent of the vehicle characteristics, as we don't have any coefficient or any parameter regarding to the vehicle. So this is what now we have arrived the complete value of SHD. SHD is nothing but this is the complete value of SHD, which is going to account both lagging distance and which is also incorporated with braking distance, which is nothing but lagging distance is equal to Vt plus braking distance is equal to V square by 2GF, where F is nothing but longitudinal coefficient of friction and G is nothing but acceleration due to gravity. So F again is longitudinal coefficient of friction. It is going to depend upon the speed. If the speed of the vehicle is greater than 80 kmph, higher the speed, lesser will be the coefficient of friction. So the amount of friction felt will be lesser when the speed of the vehicle is higher. So we have to required to take the value of 0.35 when the speed of the vehicle is more than 80 kmph, and if the speed of the vehicle is less than 80 kmph, you can take the value of F is equal to, you are going to have higher contribution of friction, which is nothing but 0.4. Of course, this doesn't have any units, so that is only a coefficient of friction. It's a coefficient value. So with this, we are going to solve this numerical question. Calculate the SHD on a national highway, which is existing on a plain terrain for a design speed of 100 kmph. Here in the question they have given the design speed of 100 kmph, but sometimes they will not give the speed also. Based on understanding the nature of the highway along with the type of the terrain, you should be able to understand what is the ruling design speed and what is the minimum design speed. So you have to refer to the table tabular column regarding the speeds in order to have the value of the speed. Luckily here they have given the speed of the vehicle, so you have to take the speed of the vehicle. So again, so here we have to calculate what is the value of SHD, which is going to have lag distance SL plus SB. I am dividing this into two portions. One is nothing but lag distance and other one is braking distance. Lag distance. So wherever in the equations I have written, so here all V is corresponding to meters per second and capital V is nothing but corresponding to kmph. We have derived our stopping side distance either lag distance or braking distance in terms of meters per second, but the question is given in kilometers per hour. So for which we have to convert the value of a kilometer per hour, speed kilometer per hour, into meters per second, which can be done by 100 divided by 3.6. This you can easily do by converting that kilometer into meters, multiplied by 1000 divided by 1 hour into seconds, which is nothing but 60 into 60 seconds. So which you are going to get somewhere around 27.77 meters per second. So the lag distance is equal to SL is equal to V into T. Okay, the reaction time, as I have mentioned earlier, which is nothing but 2.5 seconds. So this is nothing but 27.77 multiplied by 2.5 seconds is the lag distance. And coming to the braking distance, SB is equal to V square, that is nothing but 27.77 whole square. Many of you will forget to write the square value here. V square divided by 2 into G 9.81 multiplied by F. As the speed of the vehicle is greater than 100 kmph, we are going to have a lesser value of longitudinal coefficient of friction, which is nothing but 0.35. So once you calculate the value of braking distance and the lag distance, you are supposed to get the value of stopping side distance as a whole put together, which is nothing but somewhere around 190.98 meters. So this is what the stopping side distance required when the vehicle is traveling at 100 kmph. Okay, so on a given national highway, which is on plain terrain. So next, effect of gradient and brake efficiency on stopping side distance. So for the discussion, what we have done is nothing but we are discussing the stopping side distance on a level road. So this is nothing but level road, assuming that there is no gradient. Of course, gradient is approximately 0, and assuming that when we have applied the brake, okay, so the vehicle has come to stopping condition with a full efficiency of 100%, but the brakes may not be 100% efficient. So because of which you are going to have an increment value in braking distance. Okay, so that is why you are going to have an effect of gradient over here. So one side it is nothing but gradient effect, and next one it is nothing but brake efficiency. Okay, so your gradient effect is going to felt, or it is going to have an effect only on braking distance, because your lag distance will not have anything regarding to effect of gradient, or it is not going to have anything related to a vehicle. Okay, so the same way SSD is equal to VT, so this is nothing but regarding to the lag distance, plus V square divided by 2G F plus or minus N. Okay, so I'm going to incorporate some parameter which is nothing but N percentage, that is nothing but gradient. Okay, so that should be added or subtracted to the longitudinal coefficient of friction, where N is nothing but gradient, which is expressed in percentage. If it is 3%, which is nothing but the value of N is equal to 0.03. You have to take the value of plus for upward gradient, and you have to take the value of minus for downward gradient. Example, you are traveling on an upward gradient. So initially the weight of the vehicle is completely acted vertically downwards, but because of moving on upward gradient, the weight of the vehicle, some part of the weight of the vehicle is going to act in the opposite direction, because of which there will be some weight compensated here. So because of which you are going to have reduced value of this braking distance. You are going to have reduced value of braking distance. So upward gradient will have lesser braking distance. Upward gradient will have somewhat lesser stopping side distance when compared to that of the level road, and downward gradient is going to have somewhat higher stopping side distance when compared to that of level road. So this is the effect of gradient. And similarly, effect of brake efficiency, stopping side distance is equal to again Vt plus V square divided by 2G F as it is multiplied by eta symbol, that is nothing but efficiency. This is the symbol for efficiency, as efficiency will be less than 100%. So if you multiply in the numerator, this braking distance is going to be reduced, but with the lesser efficiency, the braking distance generally increases. So that is why we have to incorporate the value of the efficiency at the eta symbol in the denominator. So the denominator, instead of being 1 2GF, it will be reduced when compared to 2GF. So as a result of which the entire braking distance is going to be increased by some extent. So because of lesser brake efficiency. So that is what the effect of brake efficiency. Okay, whatever it is, if it is 100%, the original condition 1 what we have derived is nothing but this is going to be 1. Similarly, this is nothing but 0. So if you incorporate both of them to be 0, so this is what you're going, this is going to be 1 and this is going to be 0. So f plus 0 multiplied by 1. So that is nothing but the original condition. Okay, and what about the condition when we are having the effect of both gradient and efficiency? So that is nothing but SHD is equal to Vt plus V square divided by 2G F plus or minus N, that is small n, multiplied by eta. So this is what the combination of effect of gradient and brake efficiency on stopping side distance. So now we are going to solve one problem on the effect of gradient. So there is again the same problem. Calculate the stopping side distance on a national highway with the plain terrain for 100 kmph and an ascending gradient of 3% and a descending gradient of 4%. So as we have solved in the question 1 previously, one question where the stopping side distance is equal to 180 meters approximately, which is nothing but on a level road. Now we are going to calculate on this, which is nothing but an ascending gradient. I'll take this as 2. So that is nothing but ascending gradient of 3%. So where your formula will become SSD is equal to Vt, which is nothing but 27.77 multiplied by 2.5. There won't be any change in the value of lag distance. There will be only change of braking distance. V square 27.77 whole square divided by 2 into G 9.81 multiplied by F. As again the speed is 100 kmph, it is greater than 80 kmph, where you will be having reduced value of longitudinal coefficient of friction multiplied by, so this should be multiplied plus or minus, as this is an upward gradient. I should add the value of 3%, 0.03. Okay, so the value is going to be 172.16 meters. So as when compared to the stopping side condition and level road, the value of stopping side distance has been reduced on the upward gradient. So this is upward gradient. So therefore the value has been approximately reduced by 8 meters. And when compared to the second condition, we will be looking at the third condition, as descending gradient, so which is nothing but descending gradient of 4%. So therefore you are going to have the same value in terms of lag distance, 27.77 multiplied by 2.5 seconds plus 27.77 whole square V square divided by 2G, G is nothing but 9.81 multiplied by 0.35 F minus, as I told you, for downward gradient or descending gradient you have to take the negative symbol, F minus N, 0.04%. So this value is going to be increased by 195.04 meters. So this value has been increased to the static condition by approximately 15 meters. So this is what the effect of gradient, here, ascending gradient and effect of descending gradient. So next we have a question in combination of both ascending gradient as well as brake efficiency. So there is an ascending gradient. Because of the ascending gradient we are going to have the reduced value of this stopping side distance, and because brake efficiency is less than 80%, we are going to have an increased value of stopping side distance. So again the formula will remains constant. SHD is equal to Vt brake distance plus V square divided by, I'll write the whole formula, 2G Fr plus or minus N whole multiplied by eta. So that is nothing but 27.77 into 2.5 plus V square 27.77 whole square divided by 2 into 9.81 multiplied by F is nothing but the same F value, 0.35. Whereas if it is an ascending gradient, so it will be plus 0.05 whole multiplied by 0.8. This should be taken in 0.8. So with that we are going to get the value of stopping side distance in combination of both gradient as well as brake efficiency, which is nothing but 191.46 meters. So generally with introduction of ascending gradient, the stopping side distance should be decreased when compared to 180 meters. But as a result, when the braking efficiency is been only 80%, again the value got increased by 10 meters. So this is what the effect of gradient and braking efficiency in combination. So next one, we have an intermediate side distance. So far what we have been discussing is, we are assuming that there is only an obstruction in the opposite direction. In the at a static condition, that is an obstruction which is at a height of 15 centimeters. But let me assume that there is another vehicle which is coming in the opposite direction, which is not permitted in one lane carriageway. But let us assume that there is a condition. In that condition, this vehicle has to travel some distance to stop the vehicle, and this vehicle has to travel some distance. Okay, this distance is combined of both lag distance and braking distance of this particular vehicle. So which is nothing but vehicle 1, and this is nothing but vehicle 2. Okay, and this is the distance traveled by the vehicle 2. So therefore, that is what. So somewhere they point, both of them will be meeting at some point approximately, such that they will not undergo collision. Previously, this is constant. Only this entire part is created by the vehicle 1. But whereas this vehicle is in the opposite direction, is also in movement. So they both has to come somewhere in the middle and intersect at some point, or should stop at some point, such that they will not be under any collision. So that is what SHD1 plus SHD2, assuming that both the vehicles are traveling at different speeds, V1 and V2. That is the only condition. Okay. So in the first general condition, that is nothing but it is traveling on a level road with obstruction only. So therefore you are going to have only SHD1 with some single speed. But whereas the vehicle which is moving on opposite direction, so that is why this is said to be intermediate side distance. If both the vehicles speeds are traveling at same speeds, then it will become SHD1 plus SHD2. As both of them are same, you can take it as SHD, which will be 2 times of SHD. So that is nothing but intermediate side distance. So the condition is nothing but very, very important. So that is nothing but calculate, what he will be given is nothing but calculate safe SHD. He will not give it as ISD. Calculate safe SHD on one lane two-way traffic. So one lane two-way traffic. So if it is only single lane carriageway, okay, and it is two-way traffic, then only the vehicle will be coming in the opposite direction. Okay, so as a result of which we are getting SHD, safe SHD. Of course, safe SHD is equal to 2 times of SHD, which is nothing but ISD. So we have one more problem on this intermediate side distance. Calculate the intermediate side distance on a national highway with plain terrain with the vehicles moving in with speed 70 and 90 kmph respectively in opposite direction. This is important, in opposite direction. So that is what. So there is a vehicle 1 over here. There is a vehicle 2 over here. Okay, of course vehicle 1 is traveling at a less speed. Okay, let this be vehicle 1 which is traveling at V1 speed, and this is the vehicle 2 which is traveling with V2 speed. Therefore SHD for vehicle 1, SHD1 is equal to VT. Of course you have to convert that 70 kmph in meters per second, so which will be 19.44 multiplied by 2.5, which is nothing but the lag distance, plus V square 19.44 meter square, V square divided by 2 into 9.81 multiplied by F is, if the speed is less than 70 kmph, we are going to take the value of longitudinal coefficient of friction as 0.4. So that is what you are going to get the value of stopping side distance as 96.75 meters. And whereas the SHD2 is equal to, that is the stopping side distance corresponding to the vehicle moving in the opposite direction, which is at a speed of 90 kmph. So you have convert this 90 kmph in meters per second, which will be 25 meters per second. So therefore you are going to have the value VT 25 into 2.5. This is speed and this is reaction time, plus distance, speed is nothing but V square divided by 2 into 9.81 into the speed is nothing but 90 kmph greater than 80. So you are going to have only 0.35. So as a result of which you are going to get the value of stopping side distance as 153.57 meters. So therefore ISD is equal to SHD1 plus SHD2, which is nothing but the value has turned out to be 250 meters. So I conclude the session on stopping side distance over here. Have a great day.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.